Hello, everybody. This is a talk about replacing flow dissector with PANDA Parser by Tom Herbert. Tom is going to be joining anytime soon. What we'll do is we'll start with a video, and Tom will be here for question and answers after after the video. So do post your questions in Q&A, and we'll get to them. I'm going to play the video and hide myself.
Hello, my name is Tom Herbert, and with me today is Pedro Tamala, and we will be talking about replacing flow dissector with the PANDA Parser. The agenda for today's talk, first we'll go a little bit into the background of flow dissector, cover some of the basics of the PANDA Parser, then we'll show how we put PANDA Parser into the kernel and created the PANDA TC classifier. After that, we will show some performance results comparing flow dissector and PANDA. Following that, we will look at some of the future, some of the different directions that we might be able to take, and we'll end with providing some PANDA project information. So let's start with looking at flow dissector. Flow dissector is a Linux kernel function. Is defined in some of the BPF documentation as a routine that parses metadata out of packets. And it's used in various places in the kernel networking subsystem, RFS, flow hash, etc. So this is a kind of key function, and it's been developed over quite a few years. If we go back in time and look at the origins of this, it actually goes back to, I believe, a patch that I had done in 2010 for receive packet steering. This was a very simple flow dissector. We didn't call it that at the time, but the idea was we want to extract IP addresses and UDP port numbers, TCP port numbers also, from packets in order to create a hash that we use to steer packets in RPS. It's very similar to the RSS hash that is computed by devices for RSS. So that was the initial instantiation. It was about 40 lines of code. The next year, Eric Dumazet looked and saw that we had a couple of kind of competing functions doing basically the same thing. So he created SKB flow dissect, which is really the modern day flow dissector. As part of this, he introduced the concept of flow keys, which was a convenient way to organize and store metadata. And also, we greatly expanded the number of protocols that can be parsed. We added 802.1q, PPP, GRE, IPIP, and a few others. Skip forward 6 years later, and Juri Perko added a very key patch, which allows flow dissector to be programmable. And what's really programmable in this is the flow keys can be specified by the caller. So basically we can program what metadata information is collected of all the possible metadata information. So from that point of view, it is programmable. However, it's not programmable from the point of view that a user is allowed to add their own custom protocols to flow dissector that could be parsed. But in 2018, Peter Penkov implemented a BPF hook to flow dissector, which mostly allows that sort of programmability. So now we can write an eBPF program, hook it into flow dissector, and the eBPF program can programmatically parse new custom protocols in flow dissector. The kind of problem with that is it's not really integrated into flow dissector. So it's kind of either or. Either we call into the eBPF hook or we use the canonical code in the kernel to do flow dissector. So skipping forward today, flow dissector is probably one of the bigger functions in all of Linux networking. It's about 1,200 lines of code. It's mostly in flowdissector.c. As I mentioned, we have BPF support. There is sort of tunnel support. It's not really first class. We'll talk about that in a bit with regards to UDP. There's about 10 callers of the function, and it spreads TC classifier. Some drivers use it. It's still used for the SKB hash going back to the RPS origins. So one of the critical aspects of flow dissector that's represented here in this parse graph is that flow dissector really does implement this sort of parse graph. So the root node to this graph is Ethernet. Below that, we have a proto switch that spans out to the different ether types. If the protocol ether type is IPv4 or IPv6, then we actually can do a switch on IP protocol to identify TCP, UDP, IPIP, etc. Some of these nodes are actually encapsulation nodes, and these are indicated by the red backlinks to the ether proto switch or the IP proto switch. So when we parse a packet that contains encapsulations, we may want to follow the encapsulation, and that basically entails going backwards in the graph and starting over at a different point. So for instance, if we have an IP and IP encapsulation, the first time through the graph may be processing the outer IP headers. And then in the IP encapsulation, the second pass may be processing the encapsulated IP headers. So flow dissector and SKB flow dissect, it's very powerful, very impressive function. It's probably one of the most complete and efficient parsers in networking today. However, I like to view it as a function you love to hate. And why is this? Well, first of all, flow dissector, I think by any standard, we have to call it spaghetti code. It is really, really hard to write what is fundamentally a parse graph and effectively a finite state machine as a sequence of imperative code that looks reasonably structured for the problem. And in addition to that, trying to basically implement a parse graph into C code, one of the major problems that we've noticed over the years is that the bookkeeping that's required for each protocol that we parse is very prone to errors. And this bookkeeping specifically is things like when we encounter a protocol header that we're parsing, we have to determine the length of the header. And then we have to determine if that length actually falls within the expanse of the packet. So in other words, we can't parse a header if it doesn't fit into the packet. So each time we hit a header in flow dissector, we have to check the length, which is probably something like an SKB pull up to load it into linearized header buffers so that we can immediately parse the headers. So this one thing has actually created a lot of problems, especially when new protocols have been added that are a little more fringe and don't get a lot of testing. So we have had issues there. One of the other issues that I did mention is flow dissector really doesn't parse UDP payloads. This is particularly problematic if we want to go into UDP encapsulations. So for instance, if we want to parse the encapsulated packets in VXLAN or NVMe, NVGRE, we can't do that in flow dissector. There's a kind of way to do this with ancillary tunnel information, but that has to be provided by a third party. Also, we may want to parse QUIC or other UDP protocols. Fundamentally, adding new protocols to flow dissector is very painful. Basically, we have to change the kernel. It's a kernel rebuild and install, so all the pain of kernel rebase is there. But this has a side effect that things that use flow dissector in user space, like TC-Flower, they're basically bound by this also. So it's also difficult to add new protocols to TC-Flower for the same sort of reasons. And this problem extends to programmable hardware. So say we wanted to offload flow dissector into the kernel, then because it's hard to add new protocols to flow dissector or offload into hardware, then because it's hard to add new protocols into the kernel flow dissector, it would be equally difficult because of the APIs to add new protocol support in programmable hardware. One other problem that kind of came up recently, the metadata structure for flow dissector is rather rigid. So it's kind of predefined and hard to find. One of the obvious things is it's very constrained on how much information can be contained. And this shows up particularly in the case of encapsulations. So right now, flow dissector is capable of, say, storing the inner IP addresses and the outer IP addresses of encapsulation. But say somebody wanted information about a middle encapsulation, like we were doing 3 levels of IP encapsulation, then they wanted to know the middle one. Right now, there's no way in flow dissector to represent that. There's other problems in flow dissector that we may have one value in the metadata that really could refer to multiple instances of that protocol in flow dissector. For instance, we're limited in the number of VLAN headers that we could record metadata on for that reason. So flow dissector, as impressive as it is missing quite a bit of protocols that are definitely of interest in modern day networking stacks. So some of the things that are missing, first of all, I mentioned the ability to parse UDP payloads. What we really want is when we parse in the UDP, identify probably the destination port and determine if that's some sub-protocol, be it QUIC or Genev or VXLAN that we want to parse into. And in the case of UDP encapsulations, we would want to follow that and parse the encapsulated headers. Another thing that's obviously missing is the ability to process and parse options, such as TLVs. TLVs are very predominant in TCP. They're also used in some encapsulations. They're becoming more integral into IPv6 and destination options and hop-by-hop options. And there's also a proposal on IETF for UDP options. Unfortunately, flow dissector doesn't process these. And in fact, there's a lot of hardware parsers and other implementations that kind of skip these. One of the rationales is that this is a hard problem. Parsing something like TLVs is known to be difficult. It's hard to do that because of its inherent serialization. But nevertheless, there is still a need, I believe, for this sort of parsing. Another area is upper layer protocol parsing. So this becomes evident if we want to apply this sort of parsing methodology and metadata extraction to upper layer protocols, say an RPC that's embedded in TCP. So we have to basically extract from the TCP stream PDUs, and now we may want to parse those PDUs using a parser like the same functionality of flow dissector. So that's about flow dissector. And now we can look at the PANDA Parser, which actually addresses most of the issues that we just talked about, but it's intended for a much broader application than flow dissector. So the PANDA Parser is a fully programmable parser with not only a C and C++ front end. So we chose C and C++ because it allows easy integration with the stack. It's hard not to notice that most networking software written today is already in C and C++. Obviously, the Linux kernel is. So our idea about that is the PANDA Parser written in that same language will maximize the amount of integration with existing stacks. That being said, other front-end languages are possible. I'll touch a little bit about that in the next slide. In the PANDA Parser, we define the parser not really by an imperative sequence of instructions, but more as code containing a declarative representation. And this manifests itself as a set of C data structures that are linked together in a parse graph. Nodes in the graph can be annotated with operations that are necessary for parsing and metadata extraction. One of the big advantages of PANDA really is that we're targeting arbitrary backend and hardware software targets. And this gets or motivates our motto, which is write once, run anywhere, run well. Write once, run anywhere being taken from the old Java mantra of the 90s. That gives us ubiquity and the idea that you can write a program once and run it on various targets. We added the run well clause because it's not enough just to be able to run the programs. For any given environment, we want to optimize execution and use the resources to the best effect for that particular environment. But one very critical thing is that we want the same exact code to run across different targets. So we believe that other than a recompile, to run between software targets, even run the code on different hardware targets, the user should not have to change their code. This is absolutely critical for adoption and ease of use for users. There's some additional features. I mentioned TLVs being a problem in flow dissector. We actually are treating TLVs as first-class citizens in PANDA. Metadata frames is a concept that instead of metadata being a single structure, we can actually make an array of frames where each frame can correspond to one layer of encapsulation. So if I have 3 layers of encapsulation on my packet, I can have 3 frames and then get all the information about those independent layers into those 3 frames. The technology that really ties a lot of this together in our implementation is the PANDA compiler. This is a type of compiler that would translate this target agnostic front-end code into that optimized executable per target, being hardware or software. The programming model, I will touch a little bit about this. I actually went through this at last NetDev, but as I mentioned, a parser is composed of a set of nodes linked together as a parse graph. The nodes of the parse graph are the protocols to parse. Each node contains protocol operations that are required for parsing. There's really 2 operations that we're talking about here. One is the length of the current header. One is the next protocol. Given these 2 pieces of information, that's actually sufficient to parse nearly all the protocols that we've encountered. In addition to those operations, callbacks in each node allow for metadata extraction and the custom processing of protocols. And the additional construct that we need are tables that map protocols to next nodes. These are fairly simple tables that, given a protocol number, they just return a pointer to the next node structure. The development of path for making a PANDA parser program is pretty simple. So the user writes a data path program in C and C and C++. Again, in C, this is a sequence of, really can be done as a sequence of macros that create a fairly small program that has a lot of power. As I mentioned, other front ends could be used. So we could create a parser out of Python, Rust, P4 with the right implementation. There's also an interesting concept, since a parser is really a declarative representation, or can be done as a declarative representation, it really works well to be represented in XML and JSON. That assumes that those protocol processing operations can be represented as some sort of parameterized function, simple function that we can encode as instead of encoding as instructions, we can encode that as a data set. That's actually pretty true for nearly all the protocols. So we may in fact end up using XML and JSON, and that actually might be a nice intermediate representation for the PANDA parser. And that also has a nice side effect. It makes it very easy to integrate that into an IDE or GUI for writing programs. So once the code, whatever the source is done, it goes through the PANDA compiler. In the case of software target, we support XDP, BPF. We support DPDK. It's probably something that we haven't tested, but nevertheless, it's a pretty simple user space code that we have should work. And our other newest member of the fleet is supporting this in the Linux kernel. So that is primarily what we're talking about today. The software, though, is the only one possibility. We also, as I mentioned, allow the possibility of hardware. A hardware engine that can consume the PANDA parser and produce a very fast parser is actually what my company, SciPanda, is working on. The idea, again, because this is write once, run anywhere, is that the user could write their parser once. They can run that exact same code on any of these environments, including the hardware, and see no functional difference. Presumably, when they put it in the hardware, they should see a drastic performance improvement, which is the whole purpose of putting it in the hardware anyway. So looking a little more at the kernel side of this and building PANDA parser into a kernel module, there's really 2 parts, 2 pieces of code that the user would start with. One, again, is the parser program, which is agnostic. So this could be any parser program that the user is interested in. We have an example in our code base called bigparser.c. The other component of this is really module code. It's the specific kernel module code that glues the program into the kernel It would include the TC hook implementation and what have you. The kernel program is really what would invoke the PANDA parser, and that is done by the command highlighted in purple, PANDA parse. That simply takes a name of a parser and some fundamental information about the packet, packet length, pointer to the metadata, and a couple of flags. So these two things together define the kernel module that invokes a PANDA parser. We run the parser program through the compiler. That produces an optimized kernelized C code, which in our model we call parser.kmod.c. That is the thing that's ready to be linked with module.c to actually produce the kernel module. So we run both of those through GCC. That outputs KO loadable module, and that's the module we can load in the kernel. One really nice thing I should mention, by the way, is when we go from this source code to the optimized C code through the PANDA compiler, we are really relying heavily on some of GCC optimizations, especially the later versions of GCC are really good at optimizing out things. For instance, in a static constant data structure, GCC is now able to actually inline functions within that. Function callouts can be inlined, and that's a huge benefit for performance. Turning now to the PANDA classifier, which is our really first use case of the kernel, PANDA in the kernel. So this is pretty simple code. So we have a classifier that would be written by the user following the rules we just mentioned. When it's compiled and loaded, the first part is to register the parser to the classifier. This is done through an easy TC filter rule. And then we need to associate parser X to filter Y so that filter Y can invoke parser X. And that's fairly simple also. We then invoke parser X to do classification. So this, on a received packet, goes to TC. We call the parser. That invokes the PANDA parser, extracts the metadata, and then we can use that metadata in part of the classification rules in TC. A lot of this came from the ActIF scheduler code. So if we put all this together, we did do some performance testing. This is basically testing flow dissector versus PANDA using kind of a synattack model where we're actually just dropping packets on receive. So it's somewhat of a standard XDP sort of test. We are going to compare three different things. So one is FlowDis and one is the regular PANDA parser. That PANDA parser would basically emulate and provide the same metadata as FlowDis. The third one is actually a stripped down version of the PANDA parser where we're really only extracting the flow tuple information that we would need from a normal use case of a TCP synattack mitigation. So we compare these three. On the left, the y-axis is the percent CP utilization. On the right, we have the y-axis for the secondary measurements to be drops per second and 1,000 packets per second. Our horizontal axis shows various loads in millions of packets per second from 2 to 2.5 or 2 to 3 in increments of a quarter million packets per second. So what we see here is that if we start at 2 million packets per second, PANDA and the PANDA 5 tuple have significantly lower CP utilization. There's no packet drops yet, but we are shaving off a few percentage points from flow dissector. And you have to remember that there's a relative thing happening. This is measuring, these measurements include the full stack CP utilization. So the relative gains here between PANDA and flow dissector are fairly significant. If we go to 2.25, we see a similar advantage to PANDA and PANDA 5 tuple. At 2.5, they actually look the same. I think this has to do with some of the amortization of interrupts. But once we go to 2.75, we now see that all three have 100% CP utilization. And we actually start to see packet drops in the FlowDis case and a very tiny number in the PANDA case. Once we go up to 3, then we see even more drops in the FlowDisk case, some number of drops in the Panda, and some number in the Panda 5 tuple, but they are still less. So I should mention in all these cases, lower is better in both CPU utilization and packet drops per second. So turning to the futures, so the Panda in the kernel, this is actually our latest release. The code is should be released by today, hopefully after I record this. So we have some extensions in mind. So one interesting thing would be to use BTF. So Panda, since it is programmable and the metadata format in particular is programmable, it allows a wide variety of customization in both what the metadata contains and how the metadata is formatted. This does create kind of the well-known problem, consumer-producer problem, where if someone is consuming data of a certain structure, we have to synchronize the consumer to make sure that it understands that data. So I think in some cases, BTF may fit the bill to solve some of that. And that's definitely something that we will be looking at. One of the other ideas that we've had, this may have been discussed briefly or at last NetDev, I think it was brought up in a couple of presentations so far. We really want to have what I call generic TC flower. So as I mentioned, TC flower is quite limited today. It's really bound by kernel flow dissector, what it supports, and also putting new protocols into TC flower user space itself requires quite a bit of work. We really would like to see this be flexible. So if a user, for instance, has their own completely set of custom protocols, they really don't want to have to go to the kernel, make all the changes, get in the flow dissector, and go through that long path. Obviously, I think what they want is they want to create this on the fly, load a programmable parser, fix up TC flower so that they can specify the fields for their own protocols and parse them. That's the idea of generic TC flower. The plan is we will take a Panda Parser program, compile it, load the program into the kernel, like in the kernel module, but also have the Panda Parser compiler produce a specification file that associates human readable names with new fields or fields in the Panda Parser. And the TC flower binary, user space binary can consume this, and then it can create both the front-end command line API to create new fields for custom protocols, but it can also send those into the kernel in an abstract fashion such that we can synchronize, again, the producer and the consumer of the metadata structure. And linking all this together, this is how we can accomplish a very dynamic, very adaptable generic TC flower. The topic of this presentation is to replace flow dissector. This is on the horizon, I believe. It's obviously takes a little bit of time. Flow dissector is something that was not developed overnight, and there's quite a bit of reliance on it. But I do believe with the ability to make it programmable, code cleanup, and better performance, that this is something that we do want to pursue. So it may take a little bit of time, but I think it would be great to somehow sunset flow dissector. I mentioned a couple of times hardware acceleration, so I'm not going to cover this too much more. But I would point out one nice thing, if we do get to generic TC flower, then extending that into TC flower offload would be somewhat of an obvious direction to go. Finally, I have one more of a meta future or vision, kind of rhetorical thing. So programmable parsers like flow dissector, things we get out of XDP hints, any sort of parsers like that, the output and the processing are really not used in core stack protocol processing. They're kind of independent. So for instance, if a packet comes in, it goes through TC, we may parse that packet in flow dissector in a TC rule. If that packet is accepted and goes into the stack, all of the results and all the information from that parsing basically are thrown out, and the stack has to reparse the packet. So it starts at Ethernet, it goes through IP, TCP, any number of encapsulations. The possibility here is that we have a different model where the parser is actually integrated, so the stack and the parser work together so that we can actually optimize that component of the stack in the parsing component, optimize that out, and have a much more efficient integration. Take this into the hardware, and now we have the hardware actually participating in protocol processing for the stack. That's what we call acceleration versus offload. Panda open source information, if you're interested, we do have a GitHub. It's pandanet/pando. As I mentioned, we have 4 releases, and the last one is 1.3, which includes the kernel. Inquiries can go to panda@scipanda.io. With that, I thank you and open up the floor for questions.
Hey, thanks, Tom. Sorry, people, you had to see, well, you had to see me and you had to see the spaghetti twice. Apologies for that. Let me get Tom on stage. So how do I... Tom, you're on? Okay. I see you updating on chat that you have more updates on Panda. Maybe you can cover that and then I'll project the first question.
Video is not on.
Yes.
There we go.
Yeah.
All right.
So do you want to answer anything that you just posted on chat? You had some updates on the...
Yeah, sure. So like I said, I was planning to push the code. So 1.3 version of Panda is the one that contains the kernel code. Excuse me. So I actually pushed that during the talk, practicing the just-in-time mentality. I would also like to give a shout out to Pedro Tamala. He did a lot of the kernel code, and the folks at Mojitatu actually have been doing a lot of the implementation. We've been going, started the project with first release back in February, and it's going pretty well. We're at the point where it's, I think with this release, it's starting to get something usable. Starting an open source project from scratch is always an interesting challenge. Addressing a few of the comments. So Willem was asking about BPF versus C code in the kernel. And it's true, BPF does have some limitations, particularly when we're trying to do something complex like parsing. And what we found in our work to move or put Panda into XDP and eBPF, verifier was pretty strict in a lot of respects. So, and it wasn't the number of instructions, it was really the complexity algorithms of the verifier. It did not like, especially doesn't like the fact you're doing loops. Unbounded loops are like the first thing that's going to be thrown out, and rightly so. Putting an unbounded loop in the kernel is obviously very dangerous. So we had to come up with a lot of construct for bounded loops. We also had to look at how to deal with variable length headers. That was also kind of interesting. The way that eBPF and XDP work, they really like to have very fixed, predictable header sizes that can be analyzed by the compiler at compiler time. With the variable length protocols, that's much harder. So we actually had to come up with a solution to that. I think it's fairly elegant. So it actually is plausible, or feasible, I should say. But in the case of eBPF, we do have to split kind of the TLV processing. So I believe right now we can process 4 TLVs before we have to do a tail call to do kind of continue that. And encapsulations are kind of the same way. So encapsulations have that other aspect of potentially being unbounded or at least deeply nested. So we do need to work with verifier. Obviously, for regular kernel code, we don't have those limitations, but that's not to say that we just want to throw in things that can cause infinite loops into the kernel. One of the advantages, though, with something like the PANDA Parser and the PANDA compiler is that the code that we're producing is kernelized, which means we're taking this generic code and we're adding the stuff, the kernel specific kernel glue. So in that regard, it's actually very structured kernel code. And if you compare this to like Flow Dissector today, and as I mentioned, there's a lot of bookkeeping work. In the Panda model, the user doesn't have to do any of that bookkeeping work. It's actually handled by the engine. So the engine can apply that very consistently. And that eliminates a lot of that bookkeeping, which is prone to error. So it ends up working pretty well. And what we do think is that the code is produced should be at least of the quality of the kernel. And obviously, if we do intend to ever actually replace Flow Dissector with Panda Parser, then we have to have that level of quality. So there's no shortcuts here. We still have to do all the same thing and still have to verify the code. But we do think it could result in cleaner code. +1 on formal verification. The interesting thing about parsing, and there's really some nice papers going back, some of the work by Nick McKeon, it is really a very mathematical process and is almost identical to finite state machine. So that's one of the reasons why we really want to move towards more of a cleaner declarative representation. Comments about TC Flower. Yes, you can get tunnel information, but that's not really done from Flow Dissector. It's done from an external agent that has already parsed it. As I mentioned right now, Flow Dissector, it can't go into, or doesn't go into UDP. I actually had posted a patch to do that a while back, but I think in retrospect, just adding more and more to Flow Dissector to do more and more functionality probably isn't the most productive thing. So I think we need to look at an alternative like Panda.
Tom, questions? Yeah, the one I projected. Right
Doesn't
now.
look at the questions?
Yeah, in the Q&A tab, the one I projected.
Yes.
On, and there's another one.
Oh, okay. So you brought up the screen. Are the parsing nodes stateless, or is it possible to have something like eBPF maps? The parser itself is stateless. However, that can be easily annotated by the handler functions that I mentioned. So for instance, one thing we may want to do is if I have if I have a TCP connection, obviously, that I want to parse, then I do have to look up the state at some point to extract the streams and extract information. So eBPF maps obviously are eBPF specific. If we were doing this in the kernel, then potentially you would want to have some configuration, which may be eBPF maps or something else. But fundamentally, when I look at Flow Dissector itself and replacing it, Flow Dissector is stateless right now, so we would want to go that same direction, at least for a short term. For replacing the Flow Dissector, you envisioning upstreaming a particular parser output by Panda? It's a very good question. And I think the answer to that probably would be yes, especially if we're replacing the core Flow Dissector. But the caveat here is that one of the reasons why Panda is faster than Flow Dissector is because a particular instance of Flow Dissector is very specific. So what that means is we don't have to have all the conditionals to check if keys are set. So for a particular instance of Flow Dissector, the caller specifies the metadata and the program exactly, and that's exactly what you get. So we would need effectively to have an instance per caller or Flow Dissector, per unique caller, to extract different information. So, and that's not too much of a problem. Obviously, that generates a little bit more code, but there is a nice trade-off. We get a lot more performance that way. So for actually replacing Flow Dissector, I do think we would want to have the kernel code kind of produced, because obviously anything going to the kernel itself has to be verified. So there's not, in that mode, if we're integrating this into the kernel itself, I don't think we can have a lot of dynamicism. On the other hand, like our first instantiation, this is done in the kernel module, which works really well. So we can add kernel modules easily, like classifiers. In that case, we have a little more latitude to do this dynamically. Expanding, okay, next question. Expanding on BPF kernel module, given that you have a kernel backend anyway, why do you need both BPF and kernel module? Well, I mean, it's the same reason why we have a flow dissector in a kernel today and a BPF flow dissector. They serve different purposes, have different flexibility, different functionality, different histories, and also different performance characteristics. And I could easily turn this question around and say, if we have BPF, why do we need kernel code at all? Kind of a snarky question, but I'm sure that's been brought up before. Yeah, BPF is very powerful. We want to fully support it, but there are instances, especially for the core performance, where we do want to have a parser in the core kernel code. And also, we already mentioned the complexity and the problems, or not problems, but the interesting challenges of getting complex code through the verifier. And you don't really need that in all cases. So we'll live with both worlds. And as I said, the core tenet of Panda anyway is that it's agnostic. So we'll happily run in XDP, BPF, DPDK, kernel, hardware. They're all the same. As long as that front-end program that the user is writing, as long as they have the ability to run on their favorite environment, that really is the important thing about Panda. So just think of this as one instantiation. The reason I wanted to talk explicitly about flow dissector is it is, kind of the function that we really want to target because it is, like I said, it's really big and it's really caused a lot of problems. And I think we can move it forward with something like this.
Tom, we're almost a bit out of time. And yeah, if people have questions, maybe, grab a table at the lounge. Thanks a lot, Tom.
Okay, thank you.